So far, all of the examples of groups that I've had you look at in this class have been commutative groups, meaning the group operation is commutative, which begs the question, are there non-commutative groups? And that's the goal in this next set of videos, is to find a concrete example of a non-commutative group. The group that we're going to be looking at is an important group. It's based on linear algebra, but I want to make this a standalone example, so I'm going to start with some basic definitions from linear algebra and not expect you to remember any fancy theorems from linear algebra. So I want to start with a very basic definition. The determinant of a 2 by 2 matrix is nothing more than the product of the main diagonal minus the product of the off diagonal. So the determinant of this matrix would be AD minus BC. The other basic definition that I want to remind you of from linear algebra is the way we multiply two 2 by 2 matrices. So if I have these two matrices and I want to multiply them together, the answer is going to be AE plus BG, AF plus BH, CE plus DG, and CF plus DH. And the basic way that you're doing the matrix multiply is to get this particular entry, you're going to dot the first row of the first matrix with the first column of the second matrix. To get this entry, we are dotting the first row of the first matrix with the second column of the second matrix. This entry of the product matrix is the second row dotted with the first column, and this final entry is the second row dotted with the second column. And so that's how you can quickly do matrix multiplication. I also want to define a set that you probably haven't seen before. So we are going to define the set GL2 to be the set of all 2 by 2 matrices such that the determinant of the matrix is not equal to 0. And I claim that GL2 under matrix multiplication is a non-commutative group. Well, the first thing is that we have to show that this thing is a group, and I want to talk a little bit about the strategy for doing that. So the strategy to show that anything is a group, we need to show that GL2 under its multiplication satisfies all of the group axioms. We have to show that it satisfies closure. We have to show that it satisfies associativity. We have to find that there is indeed a right identity element. We have to be able to find a right identity. And we have to show that right inverses exist for every element inside of my set. Now, it turns out that there's a fair amount of tedious but critical algebra that needs to be done to show closure and associativity actually do work in this particular algebraic structure. And we're going to deal with closure in this video, associativity in the next video, and then I think the third video is going to be the right identity and the right inverses, because they're much easier actually. So I first of all want to talk about what closure means. Well, we have to let A, and I'm going to let A be this matrix, and B, which is going to be this matrix, E, F, G, H, be any two elements of GL2. We need to show that A times B also belongs to GL2. Now, I do know that if I multiply the two matrices together, I'm going to get another 2 by 2 matrix. When we multiply these two matrices together, we get AE plus BG, AF plus BH, CE plus DG, and CF plus DH. This is certainly a 2 by 2 matrix, but that's not enough to guarantee closure. The question is the determinant of the product not equal to 0? Because we have to have that before we have closure established. Now, I do want to make one note. If A is in GL2 and A equals this particular matrix, then I do know that AD minus BC is not equal to 0. And likewise, when I say that B is an element of GL2 and I set B equal to EFGH, then what I know is that EH minus FG is also not equal to 0. The question, however, is whether or not the determinant of this guy is equal to 0 or not. Well, that's a kind of, that involves multiplying these two expressions together and then subtracting off the product of those two expressions. And we need to actually look at that arithmetic. So let's look at it. The determinant of my product matrix is the determinant of this ugly matrix. And when I do the finding the determinant, this is what I get. Now, I encourage you to stop the video whenever you want to for copying stuff down. But I also encourage you to first of all listen to the whole video so you get a feel for how the arithmetic is working. And then go back and rewatch this part of the video and copy things down by stopping it every now and then very carefully. When I multiply this out, I get this expression. And what I want to notice is that in order to deal with this expression, I'm going to need to reorder the terms and make things easier to figure out what I want to do. So for each one of these terms, I'm going to reorder the term in alphabetical order. So this first term is going to be rewritten as ACEF, and this term would be written as BCHE. And I also have to deal with that minus sign. And when I do both of those, this is what I get. And when I'm staring at this, I immediately notice a couple of important things. This term and this term are exactly the same except for that minus sign, so they drop out. Likewise, over here, BDGH and minus BDGH drop out. So I'm now left with just these four middle terms to consider what's going on. And I'm going to write the things that have AD first, and then I'm going to write the things that have the BC second. And when I do that, I get this expression. And now what I want to notice is on the first two terms, I can factor out an AD, and on the second two terms, I can factor out a BC. And when I do, I get this expression. Now, I can almost factor again, but the order of FG minus EH is backwards of this. So what I'm going to do is I'm going to factor out a minus sign, which puts a minus sign there, and it changes that to a plus sign. So my next piece of algebra looks like this. And at this point, I can make that sheet go away because then we can factor a second time. And we're now looking at AD minus BC quantity times quantity EH minus FG. And it's important to remember that this is nothing more than the determinant of A, and this is nothing more than the determinant of B. So what we actually have here now is the determinant of A times the determinant of B. And what I want to remember is that A is inside GL2, so the determinant of A is known to not be 0. B is inside GL2, so the determinant of B is not 0. And consequently, this product is not 0 because it is the product of two non-zero numbers. And that lets me make an important conclusion. The determinant of the product is not actually equal to 0, so AB is inside GL2. And hence, we know that if A and B are in GL2, then the product is inside GL2, and we have closure. So we have the first of our group axioms satisfied. Subsequent videos will look at the other group axioms.